So today, we're going to review a little bit the type 1 and type 2 error, and then I'm going to introduce the concept of power to you. And that's something that I had intended to cover last class. We didn't quite get to, but it fits in just as well with this class. And then finally, I'm going to introduce the t-distribution to you, which we've been alluding to on and off, and we're finally going to delve into it and show when to use it and how to use it, both for confidence intervals and hypothesis tests. There is a new concept called degrees of freedom that you're going to have to be able to calculate for t, and other than that difference, the calculations are going to be pretty similar to what you're used to. Just to review, the steps of hypothesis testing, they're the same for all the hypothesis tests that you do. You start by stating your hypothesis and setting a significance level. You take your sample of size n, compute a test statistic. Before it was z, now it's going to be t, and you're going to choose an appropriate distribution, either the normal distribution like we were doing before, or the t-distribution like we're going to do today, and then determine a p-value and make your conclusions and decide whether to accept or reject the null hypothesis. You'll remember that for two-sided tests, not for one-sided tests, there was an equivalence between confidence intervals and hypothesis tests. That is, if your confidence interval includes the value of your null hypothesis, then you don't reject the null hypothesis. And that's going to hold also for the t-distribution. And you'll recall that with when we were the hypothesis tests and the confidence intervals that we were building before relied on the central limit theorem. And you remember that the central limit theorem related the population distribution to a sampling distribution. It said that if you know a couple of things about the population, that is its mean and its standard deviation, then for large enough samples, you know what the distribution of means of samples of that size are going to be. The mean of those samples, so the mean of the means of the samples, I should say, is identical to the mean of the population, and the standard error of the means of those samples was related to the standard deviation in the population by this factor of square root of n. And the key thing there was that for a large enough n, that distribution of the sampling means is normal, regardless of what the population distribution is. So we're gonna relax that assumption in a couple of ways. We're going to go towards small samples today, and we're going to require that population distribution is normal. So it is a practical, real-life application where we don't necessarily have large samples, and we don't know everything about the population. Here were the formulas that you used just as a review for constructing the confidence intervals and for performing the hypothesis tests. And I'm just putting these up here so you'll have them handy for review, and you'll see how similar they are when we start using the t-distribution. So you all remember this, the relation, the type 1, type 2 error. Type 1 error is the one that we control with alpha. That's when the null hypothesis is true, but we reject it anyways. So if alpha is set to 0.05, there's less than a 5% probability of that happening. So if the null hypothesis is true, then only 5% of the time are you going to find a test statistic that would lead you to reject the null hypothesis. Then there is the type 2 error, which is where actually the null hypothesis is false. Our alternative hypothesis is true, but we fail to reject it. So you remember that in general, we don't reject the null hypothesis unless we have abundant evidence to reject it. So if we don't have enough evidence to reject it, even when we should have, that's a type 2 error. Type 2 error can happen because we because we got lucky, or we got unlucky, or we didn't have enough data to be able to have enough evidence to reject that null hypothesis. So in that analogy of the courtroom trial, if the defendant is guilty but you fail to convict, that could be because you just didn't have enough evidence. So it doesn't necessarily mean you've proven that the null hypothesis is true. And then it's also possible that you make no error by rejecting or failing to reject the null hypothesis. So you're all comfortable now with hypothesis testing, right? We perform the hypothesis test by assuming that the null hypothesis is true, that H0, and then calculating what's the probability of observing our test statistic or something more extreme, assuming that the null hypothesis is true. When we do a power calculation, we go at it differently. We actually take some alternative hypothesis and assume that that is true. And assuming that is true, we calculate what would be the probability of rejecting the null hypothesis. So we go about, if we say, okay, what if there is a difference? Now, what's the probability of us correctly rejecting that null hypothesis? And I'll show you what I mean. And I'm going to try drawing it out here first, just to take my time with it before you'll see on the notes it's actually drawn on there. But I wanted to try drawing it here. So here's H0. This is, let's say cholesterol. Oh, shoot. Oh man, I lost it. Okay, let's try that again. So under the null hypothesis, we have a normal distribution . H0 mu equals, I don't know, what's our null cholesterol level? 200, let's say. Now you'll recall that then when we go to do a hypothesis test, we'll take a sample, we'll calculate its mean, and then find out if that mean lies within the rejection regions of this null sampling distribution. So it's going to be in these tails. Let's say z equals minus 1.96 and C equals 1.96. Ah, okay, I give up. That doesn't work. I'm just going to show it to you. So blood pressure instead of cholesterol. Under the null hypothesis is that the mean blood pressure is 130 and a standard error of 2.5 for the given. So it's a standard error of the sampling distribution. So we've got these two rejection regions out here and here. Now, when we do the power calculation, we're going to say something else. We're going to suppose that in fact the true mean of the target population is 132. So it's 2 millimeters of mercury different than under the null distribution. So if that's the case, if it's 2 millimeters, or if it's 2 millimeters different, so the mean is 132, then 95% of the time, whoops. So we're going to start with this assumption that the null hypothesis is true. And remember that we're going to reject it if we get a mean that is outside these two critical regions, the minus 1.96 and 1.96. And now under the assumption of this alternative hypothesis, we can calculate the probability of getting a value in one of those two regions. Okay, so we're assuming that the alternative hypothesis of the mean of our target population, the mean blood pressure, is 132. And then we're calculating the probability of correctly rejecting the null when we're doing a hypothesis test. So this overlap that you see here is the lines are drawn according to the null hypothesis at, say, z-scores of minus 1.96 and 1.96 under the H0 distribution, but then the power is calculated using this alternative distribution. So what's going to happen if we move this alternative distribution further to the right? What's going to happen to this area? See if I can at least draw a little bit here. So let's say it's so what's going to happen to that probability of correctly rejecting the null hypothesis if that's the correct distribution? It's going to go up, right? Yeah, it's going to look like it's going to be more like 50%. So this would be a power of about 50%. Still not a very good power. It means that if this is your null or your alternative hypothesis, you only have a 50% chance of correctly rejecting the null hypothesis. Yes?
So just a quick question to clarify. Is the null hypothesis average equals 130 or the average equals 132?
130.
Okay.
Yeah, this
So
is the null.
The alternative is that the average doesn't equal 130, or the alternative is the average equals 132?
So under your hypothesis test, the alternative is just that the mean is not 130.
Right.
Right. So this it's it's probably actually better not to call this H8 because this is not a part of your hypothesis test. This is like your alternate reality.
Okay.
This is what you're going to hypothesize that the true distribution of your target population is based on a previous pilot experiment or based just on some kind of assumption.
So, where would you have gotten the 130 to begin with? Like that number based on the pilot study?
No, the 130 would be based on, like, you know, your previous large study or the population as a whole. That's, you know,
so this would be for more of a specific group.
this one on the right, this would be for some specific group. Okay. So the H0 would be like, this is the population as a whole. The H, you know, this would be like, we have smokers, we have people with 3 or more dogs in their households. You know, we are gonna do some kind of study to see if they're different than the null population.
So
Right. Yeah, let's just call it your alternative reality for now. Yes.
So is it right to say, can we think about it that the more different that alternative reality is from the hypothesis, the more likely you are to reject it?
That's right. That's right. So the more different it is, the more likely you are to reject the null hypothesis. Also, the more narrow this distribution is, the more likely you are. So let's suppose actually, that's not a good place to do it. I'm going to clear this now. Now let's suppose okay, there's one alternate reality. Here's our power. It's getting pretty big now, right? Now we have a power of something like 90% because it's more different from the null hypothesis. And here's another one with the same mean, but a narrower distribution. How could that happen? How could you get this instead of this? Yeah.
Increasing the sample size.
Increasing the sample size, absolutely. That's the most likely way you would do that. So we've increased the sample size, so we've decreased the standard error in our hypothetical reality here, in our experiment that we haven't done yet. That's the key thing about this. This is when we're doing power calculation. This is a study or an experiment that we haven't done yet. So that's why it's a hypothetical alternate reality. So what happens to the power here with this smaller standard error compared to the larger standard error? Anyone? Oh, it increases. Thank you, Emily. Yeah, the power here now is looking like it's close to 100%. If this is true, there's almost no chance that you're going to get a mean of your sample that is not within the critical rejection region. So you've got a power of almost 100%. Any questions about this? You'll get to practice this some more in lab, but the important thing is that I want you to understand what a power calculation is, because power calculations are important. You'll hear about them if you're ever involved in planning a study. People will talk about what's your power. You know, is your sample size big enough to detect this difference? And this is the concept of where it comes from. There are power calculations for different kinds of tests. It's not always as easy to visualize as this, although it pretty much is. These are the sampling distributions, and it's a comparison of overlap between your null hypothesis, your sampling distribution under the null hypothesis, and the probability of getting a sample that lies in the rejection region, given some kind of argument about your target population. So, any questions? Yeah.
Before you make the statement, the more different it is, the more narrow distribution is, the more likely you are to recheck it. Saying the difference between null and the alternative.
Yeah, or the difference between the null and the target population. The bigger the difference between the mean of your null hypothesis and the mean in your target population, the greater your power would be. Or the smaller the standard error in your sampling distribution, due probably to larger sample size, or to a less variable population. The smaller your standard error, the greater your power. So power is just 1 minus the type 2 error, because remember, type 2 error is, okay, if your alternative hypothesis is true, you fail to reject it, that's a type 2 error. But if you do reject it, probability is 1 minus that type 2 error, that's your power. So power is 1 minus beta. And that power increases as your alternative mean gets further from mu0. So mu1 here, if that would be, say, the mean of your study population. And the power increases also either as the standard deviation of the observations in the population decreases or sample size increases. Both of those things cause a reduction in the standard error. So those are, yes? Beta is the type 2 error rate. So beta is the probability of accepting H0 when the alternative hypothesis is true. So these are the really important things to know about power. I think more important even than being able to calculate them, because there are tools to help you calculate them, but there aren't tools to help you understand what it means. So the type 1 error rate stays fixed regardless of the alternative mean or the power. The type 1 error rate alpha is something that we just set. And power is something that generally we either calculate the power for a given sample size, or we calculate a sample size needed to give a certain power. Power is, as the name kind of implies, you want more of it. So the more, when you're going to plan a study, you want to plan a study that has as high a power as possible to detect the difference that you're interested in. And typical values are 80% or 90%. Not for any particular reason. Sort of like alpha equals 0.05, it's kind of arbitrary, it's just commonly used. A power of 80% or 90% are commonly used as well. So does anyone want to tell me in plain language, suppose we're planning a study to say whether smokers have higher blood pressure than non-smokers, and we're planning a study that has 90% power. What does that mean? Yep.
That the chance that the blood pressure of the smokers is different from the population blood pressure.
So
Blood pressure population.
you're very close. Remember, there's the hypothetical bit in there. So it is that if there really is a difference in the blood pressure of a certain amount, the chances of us being able to detect it in this study are 90%. If there's no difference, then we don't expect to detect it. So because it's 1 minus the type 2 error rate. So it only applies when there is in fact a true difference. And it's to protect us, it's from not wasting money and time on a study that where even if there is a real difference, we're not going to be able to see it. So you would start out by saying we want to be able to detect a difference of 2 millimeters of mercury. Assuming that there is really a difference of at least 2 millimeters of mercury, if we observe 100 subjects, this is our probability of rejecting H0. If there isn't a difference of that 2 millimeters of mercury, then all bets are off. That's fine. We don't want to reject the null hypothesis then. It's not a type 2 error to accept the null hypothesis if it's true. Oops. All right, one more summary. We've covered these. Actually, I guess one thing that we haven't covered is this increasing alpha. If you this is actually a little bit unclear. Let's call this smaller. Oh, jeez, that's so hard. I meant increasing the significance level, which is actually a smaller alpha, right? So let's call this decreasing type 1 error rate. That's clear. So that means that you have to be more confident in the alternative hypothesis, so a lower probability of type 1 error in order to reject it. So if you're requiring a higher standard of evidence, you're less likely to be able to observe that standard of evidence, all other things being equal. So if instead of alpha equals 0.05, you go down to alpha equals 0.01, does your power go up or down? Thumbs up or down? Yeah, I see one thumb. You're right. Any other thumbs? So we've lowered alpha from 0.05 to 0.01. So if we keep all other things equal, we change alpha from 0.05 to 0.01. When we make alpha 0.01, is the power going to be higher or lower? No. Yeah, power is going to be lower because it's harder to find enough evidence to reject H0 at alpha equals 0.01, right? So you're less likely, even if the alternative is true, you're less likely to reject it because you're requiring more evidence, so your power goes down. It's kind of unintuitive, eh? Let's see. How about, yeah, yes? Uh-huh. Yeah, okay, so what does it mean to lower alpha from 0.05 to 0.01? That means that if the null hypothesis is true, instead of incorrectly rejecting it 5 times out of 100, we'll only incorrectly reject it 1 time out of 100, which means to be that much more confident in rejecting, to have that much less of a chance of incorrectly rejecting, you need more evidence. So, or for the same amount of evidence, you need a more extreme sample. It's going to happen less of you know, there's more chance that you will get a sample that does not lie in the rejection region. So, you know, under looking at this, when you know, if we have an alternative, you know, or our target population has, when we sample it, it has a distribution of mean blood pressures that really is on average different from the null hypothesis. It's still, you're still not going to reject your null hypothesis all of the time, because sometimes you'll get a sample with a lower mean, sometimes you'll get a sample with a higher mean. When you happen to get a sample with, even if these are really different, every now and then you'll get unlucky and find a sample with a small mean that you don't, where you don't reject the null hypothesis. So again, the alpha, the type 1 error rate, that is when the null hypothesis is true, how frequently you reject it. So lowering that alpha means that you incorrectly reject the null less frequently. But the flip side of that is you're widening, you know, you're saying it has to be further from the mean of the null distribution in order to reject it. And the trade-off that you make there is that even if the alternative is true, you're going to fail to reject it more often, because you're creating a bigger area, a bigger range of blood pressures where you don't reject the null. Yes?
So basically, like if the null is 130 and you had you're saying that you think the blood pressure is like, say, 160, your alpha would be really, really small. But if you say, you know, you think the blood pressure is 132, they overlap more, so it's harder to tell.
So first thing, if in your target population the blood pressure is 160, it's your beta that's really small. It's your type 2 error rate that's really small.
Oh, right, because alpha would be really high because you're like, they're definitely different.
Well, alpha is just fixed. Remember, alpha is the type 1 error only happens if actually your target population mean is also 130. So if the true target population is 160, a type 1 error can never happen, because a type 1 error is the probability of rejecting the null when the null is true. If the null is not true, it's impossible to make a type 1 error.
Can you just do a quick review one more time?
Sure. So let's go back to the previous page. when you're hypothesis testing, there's a lot of hypotheticals involved in hypothesis testing. So when we're doing a hypothesis test, the z-test, the t-test, we assume that the null hypothesis is true. So our study population is no different from everybody else, for example, or if we have, a case and control, they're no different from each other. So you assume that there's no difference and calculate the probability of observing something that is as different or more different as what you see. So when you do a hypothesis test, you just draw one distribution, this null distribution. You pick places out on the extremes of that sampling distribution. And then if you get a sample with a mean that's out in those tails on the null distribution, you reject. And that's your hypothesis test. So there's just, in your hypothesis test, there's only one distribution, the null distribution. One sampling distribution, I should say. Now, in a power calculation, we actually are thinking about two distributions. We now are going to assume that there really is a difference, because remember, we assume that the null hypothesis is true when we're doing a hypothesis test, but when we're doing a power calculation, we assume that there is actually a difference in our target population from the null hypothesis. So we assume what that difference is, and that's just an assumption, or it's based on a pilot study or something, but you have to make that assumption on a study that you haven't even done yet. That's kind of the catch of power calculations. You make some assumption that if there is a blood pressure difference of 10 millimeters of mercury from the null hypothesis, then what's the probability of rejecting the null hypothesis? And you can do that by saying what are the rejection regions of the null hypothesis, and then doing a probability calculation under this alternative distribution that we've assumed. So under, remember that type 1 error, which is what we control for with hypothesis testing, can only happen when the null hypothesis is true. Type 2 error, which is the thing that we're controlling with a power calculation, can only happen when the null hypothesis is false. So those are kind of that's the big difference between hypothesis testing and a power calculation. Good. Uh-oh. The screen stopped showing. I hope not. So this was from a while ago, but yes, as alpha goes from 0.05 to 0.01, you decrease your power, because there's a trade-off. You make it less likely to make a type 1 error, but you make it more likely to make a type 2 error.